Section 10.15, Age-Specific Population Growth. Suppose the maximum age attained by any female in a population is L years and divide the population into N age classes. We define the age distribution vector xk at time tk by the vector given by x1k, x2k through xnk, where xik is the number of females in the ith age class at time tk. Then, xk is L times the previous xk minus 1, for k equals 1, 2, and so on, where L is the Leslie matrix, given by this matrix that has zeros everywhere except along this kind of subdiagonal, where we have B's and underneath the first row of A's. So you could think of it as a matrix that just has diagonal B's, zero otherwise, with a row of A's on top of it. Let's suppose that the oldest age attained by the females in a certain animal population is 15 years, and we divide the population into 3 age classes with equal durations of 5 years. Let's let the Leslie matrix for this population be L, as given. If there are initially 1,000 females in each of the 3 age classes, how about we find the number of females in each age class after 15 years? So we'll start with x0, and we're starting with 1,000 in each class, so that'll be 1,000, 1,000, 1,000. And we'll get x1 by multiplying it by the Leslie matrix L. So that'll be L times x0, so L was given by 0, 4, 3, half, 0, 0, 0, 1/4, 0. Multiplying that by 1,000, 1,000, 1,000 gives us 7,000, 500, 250. So that's what the distribution would look like after 5 years. So let's see what it would look like after 10. That'll be x2. So we'll take L times x1, and we get 0, 4, 3, half, 0, 0, 0, 1/4, 0. Multiply that by 7,500, 250, giving us x3 as 2,750, 3,500, 125. And after 15 years, that'll be x3. So that's L times x2. So again, 0, 4, 3, half, 0, 0, 0, 1/4, 0, multiplied by 2,750, 3,500, 125. And we get 14,375, 1,375, 875. So in summation, we would have 14,375 between 0 and 5 years old. 5 years old. We would have 1375 between 5 and 10 years old. And we would have 875 between 10 and 15 years old. This is how the population is divided up after 15 years. According to the Leslie model. In any case, we were able to see the behavior after 15 years, but it would be difficult to determine the behavior after, or the limiting behavior after, some long period of time without further investigating the Leslie matrix. That is, we would like to learn more about the eigenvalues of the Leslie matrix. So if we look at the characteristic polynomial p lambda, that's the determinant of lambda I minus the Leslie matrix L. If we were to go up and actually compute this thing, we have a lot of cancellation with zeros, so it actually works out somewhat nicely. You could double check that it's lambda n minus a1, lambda n minus 1 minus a2, b1, lambda n minus 2 minus a3, b1, b2, lambda n minus 3, and so on, all the way through an, b1, b2, through bn minus 1. We could also double check, I won't work out the details, but it turns out that the eigenvector corresponding to lambda 1 is x1 given by 1 b1 divided by lambda 1 b1 b2 divided by lambda 1 squared b1 b2 b3 divided by lambda 1 cubed, and so on, all the way through b1 b2 through bn minus 1 divided by lambda 1 to the n minus 1. So keeping that in mind, we really need to be able to find these eigenvalues, as we're going to see. So it helps that we have a theorem that says that a Leslie matrix L always has a unique positive eigenvalue, lambda 1. This eigenvalue is multiplicity 1 and an eigenvector x1, all of whose entries are positive. The fact that if lambda 1 is the unique positive eigenvalue of a Leslie matrix L, and lambda k is any other real or complex eigenvalue of L, that the absolute value of lambda k would be less than or equal to lambda 1 is pretty cool. It's another good theorem. However, it's not strong enough. We need that the eigenvalue lambda 1 completely dominates lambda k in order to do our work with Leslie matrices. This equal sign is actually a problem. As an example of that, let's find the eigenvalues of this Leslie matrix right over here. So let's compute the characteristic polynomial p lambda. So that's lambda I minus L, and we get lambda cubed minus 1 for this one. So then we can do some long division. Let's see, lambda minus 1. I'll fit that inside. Lambda cubed plus 0 lambda squared as a placeholder plus 0 lambda minus 1. And doing my division, lambda cubed divided by lambda is lambda squared. Then multiplying, I get lambda cubed minus lambda squared, and I subtract, and I get lambda squared. Bring down 0 lambda, it's nothing, and then again do the division, get lambda, multiply, get lambda squared minus lambda, and then I'll do my subtraction, and I'll get lambda and bring down the minus 1. So I get no, I have to plug in divide by the lambda over here, get the plus 1, but then lambda times 1 gives me the lambda, bringing down the minus 1, it tells me I have no remainder, so I just have lambda minus 1 times lambda squared plus lambda plus 1. So I know that lambda equals 1 is an eigenvalue, but doing the quadratic formula also gives me minus half plus rad 3 over 2i, and minus half minus rad 3 over 2i. So all of these eigenvalues have absolute value of lambda equal to 1. So that means that lambda equals 1 is not dominant because it's not strictly greater than any of the other eigenvalues. So this is an example of a potential Leslie matrix that doesn't have a dominant eigenvalue, which is a problem for us. Notice in this case we have that this Leslie matrix cubed is equal to the identity. So that means that x0 is the same as x3, which is the same as x6, which is the same as any triple multiple of k. This would not be possible if the eigenvalue lambda 1 was dominant, which is why we want dominant eigenvalues for our Leslie matrices. So in order to see when we'll actually have one, we have this theorem that tells us if two successive entries ai and ai plus 1 in the first row of a Leslie matrix are non-zero, then the positive eigenvalue must be dominant. So as an example, how about we find the limiting proportion of the age distribution of the population in example 1, using this new knowledge of the eigenvalues of Leslie matrices that we have. So we had that Leslie matrix was given by 0, 4, 3, half, 0, 0, 0, 1/4, 0. Let's get the characteristic polynomial p lambda. So that's lambda cubed minus 2 lambda minus 3/8. And we can factor out 1/8 so that we get 8 lambda squared, 8 lambda cubed minus 16 lambda minus 3, which factors as half times 2 lambda minus 3 times 4 lambda squared plus 6 lambda plus 1. To see that, what you can do is write out the possible roots. It takes some time. You get plus or minus 1/8, plus or minus 3/8, plus or minus 1/4, plus or minus 3/4, plus or minus a half, plus or minus 3/2, plus or minus 1, and plus or minus 3. Then you do long division with each one and see which one works. And it turns out that the 3/2 one works because if you have 2 lambda minus 3 and you do the division with 8 lambda cubed plus 0 lambda squared minus 16 lambda minus 3, then first dividing gives you 4 lambda squared, so multiplying gives you 8 lambda cubed minus 12 lambda squared. You subtract and you get 12 lambda squared, bring down the minus 16 lambda and divide again, get 6 lambda, multiply to get 12 lambda squared minus 18 lambda, and then subtract and get 2 lambda, dividing gives you 1, and then bring down the minus 3 and it goes in perfectly. In any case, this is what we end up with, factoring it. It takes some time, but we eventually do figure out that lambda 1 is 3/2. So that gives us x1 equal to 1, b1 over lambda 1, b1, b2 over lambda 1 squared, as we saw for the formula for x1. I didn't prove it, but that's what it is. So we'll set that equal to 1 let's see, B1 is half divided by lambda 1, 3 over 2. And then B1, B2 is half 1/4. And we'll divide that over 3 over 2 squared. So we get 1, 1/3, 1/18 for the eigenvector x1. So that means that in general we have xk is about, let's see, it becomes c times lambda 1 to the k, x1, and this tells us that we have, in general, xk minus 1, also approximately equal to c lambda 1 k minus 1 x1. So those two facts together tell us that xk should be about lambda 1 x to the xk minus 1, and xk is therefore approximately equal, in our case, to 3 over 2 times x to the k minus 1, right? Because if xk is approximately equal to that and xk minus 1 is approximately equal to that, the only difference between the two is the power of lambda. So we just need to multiply lambda to get from xk minus 1 back to xk. So we'll just multiply by 3 over 2. So xk, in general, should be approximately equal to some constant times 3 over 2 to the k times the eigenvector 1, 1/3, 1/18, which tells us that 72% of the population should be 0 to 5 years, 24% about should be 5 to 10 years, and 4% should be from 10 to 15 years as the limiting behavior of the population. In this example, we use birth and parameters from the year 1965 for Canadian females. Because few women over 50 years of age bear children, we restrict ourselves to the portion of the female population between 0 and 50 years of age. The birth and death parameters are as follows. Using numerical techniques, we can approximate the positive eigenvalue and corresponding eigenvector by lambda 1 and x1, given right over here. Let's interpret these results in the context of this example. So the lambda 1 tells us that if the trend continues, that eventually, every 5 years, the number of women would increase by 7.622%, because lambda 1 is 1.07622, and it's multiplying each of the x's. Then x1 tells us that in the limit, for every 100,000 females between 0 and 5 years of age, there will be 92,594 between 5 and 10, 85,881 between 10 and 15, and so on, just by reading off the values in the x1 vector.